Good morning, viewer. Welcome to our Active English. Viewers, deep beneath the ocean floor, ancient sediments hint at our Earth's magnetic field sometimes shrunk far more slowly than expected. Deep beneath our feet, a restless ocean of molten metal helps keep Earth livable. The planet's magnetic fields forms as liquid iron and nickel circulate through the outer core, generating electric currents that create a global magnetic field. And that field is powerful, but it is not permanently locked in place. From time to time, Earth's magnetic north and south poles trade positions in events called geomagnetic reversals. The story of these flames is written into the planet itself. So, as sediments settle on the seafloor and rocks cool, tiny magnetic minerals can align with the field at that moment, preserving a snapshot that scientists can read millions of years later. So, these reversals are not quick switches. They typically unfold over several thousand years as the field weakens, becomes erratic, and the poles drift across the globe before stabilizing again with the opposite orientation. Over the last 170 million years, researchers have documented about for beg your pardon 540 reversals, and many were thought to take roughly 10,000 years to complete. A new study led by University of Utah geoscientists working with collaborators from France and Japan suggests that some reversals moved at a very different pace. And the team identified examples from about 40 million years ago in which the transition stretched for long. In some cases, lasting more than 70,000 years also, but that extended timeline reshapes how scientists think about the magnetic field that surrounds Earth and helps block solar radiations and harmful particles from space. For the same, a prolonged weak phase could matter because the magnetic field acts like a planetary filter. When it falters, more charged particles can reach the upper atmosphere, potentially altering chemical reactions there and changing how energy moves through the climate system. Some effects could also reach the biosphere, especially for species that rely on magnetic cues. According to co-author Peter Liftor, an associate professor in the Department of Geology and Geophysics, long intervals to reduced geomagnetic shielding are likely influenced atmospheric chemistry, climate processes, and the evolution of living organisms.